I usually don't use a microphone, so I apologize for that right now. Today we're going to talk about being a little bit on the offense as part of our defense. My name's Keith Rayle. My background is military, 21 years. I played with nuclear weapons. I was a helicopter test pilot, threat officer, various roles. In 1997, I joined IBM, became a security consultant. I've been around World Bank, Chicago Mercantile Exchange, NASA JPL, the National Commercial Bank of Saudi Arabia. I've been in healthcare, manufacturing, power, just about every industry that you can imagine. So I've got a little bit of a depth of background, but I don't know a lot about any of it. So when we look and think about, and this is not a sales pitch, and it's not about artificial intelligence, but I've got to start there so we can talk about how we can build an offensive system against cyber criminals, one that's pertinent for today. So when we talk about artificial intelligence, it's really pretty simple at the small level, the atomic structure. What we have are layers, input and output that we can see what happens, and then in here we have hidden layers, and the layers consist of little nodes. And a node is pretty much a little dumb application that goes out and grabs a piece of information and goes back to what it was fed and looks for that information and says how much it found. The complexity comes in with AI systems in the fact that you have billions of these nodes connected to each other, and the operation is performed in a massive parallel system. So the reason they're called neural networks is because of, like the brain, we have all of these connections that go through. Every node is connected to every node going forward. Some AI systems do a single pass of information. It'll put the file in, it'll chew it, and it's done. Facial recognition uses recursive pathing. That means that information is fed back through the same layer until it resolves what it was set out to find with those little individual nodes. Let's say for a photograph, a facial photograph. The photograph may come in the first time as the standard photo. Then it may go to black and white. Then it may go to a different color. It may go large. It may go small. And it keeps getting passed through until those specific points are found. Now, the thing that those little nodes are going out and trying to find are called features. And features are the core piece of any artificial intelligence system. This is the gold. Features are the things, the point observable characteristics that the system picks up and tries to find. The individual nodes pick up a feature and go look for it. Now, the quality of these features is what's so critical to an AI system. And this is where learning and behavior gets imparted to the artificial intelligence system, because these features are stacked and weighted according to their importance and their relevance within that artificial intelligence system. This is basically how it works. So these can change over time as far as their value and get moved up and down in the stack. Now, when we talk about the node and the feature, what happens down there at that very, very small level, let's say that we have a feature that's a bottle of Coca-Cola and it has a $2 value. That value can change over time, and we have a node, the little piece in there that goes out and grabs that and looks for it in a file. And it sees 50% of that congruent ones and zeros within that file. It outputs a value of $1. So at a very small level, artificial intelligence is very simple. The complexity arises when we connect all of these nodes together, billions and billions of connections and things. Now this value changes according to how often this is seen and how important it is to what's being looked for. And I'll give you an example. If we were to think about static analysis, one of the best systems is probably an antivirus. And we're going to get into the offense of good defense in a second. But a static analysis system that would be very, very powerful to use with artificial intelligence is an antivirus, this way of looking for malware within systems. So there was an evolution of how we've dealt with malware in the past. The first thing we did was we took malware when it came to us or to our semantics or whoever was providing our signature base. They would get a malware sample and they would create a hash of it. They would put the hash in a pile. Another email comes in with something in it. You run a hash. If it matched anything, you knew that you had malware. The problem was that if one in that file, if a 1 was changed to a 0, the hash was completely different. It's non-relational, not even close. So that was a real issue there. It wasn't very good for seeking out variances within malware groupings or families, if you will. So then we went to something called the content pattern recognition approach. And what we do here is we statically unpack, unwrap, unzip files until we get down to the point of detonation without detonating the malware. And it ends up that we can find indicators of malware without detonating. We can see macros, we can see certain things. Even the URL sourcing comes into play. So all of these little bits of information can be used to determine if something's malware without even detonating it. We'll get into detonation in a second and how this ties into the offense of defense. So this is kind of what we do now. We tear things down prior to detonation, and we look for those code blocks, those little chunks, and those are the features. And those features can change over time based off of how often we see them and how many times it indicates if something's malware or clean. Now we take those code blocks and we build what you might call super signatures. And these super signatures now have these code blocks to where if the cyber criminal reuses that code, we catch it. So we have behavior and code blocks now in a static analysis that we can use. I'm not saying they're lazy. Cyber criminals have a hard time generating true zero-day attacks. What we see are zero-day vulnerabilities, but zero-day attacks with the entire delivery package are somewhat rare because if they don't use the same code, they're using the same behaviors. And behaviors get into the next aspect of this, which is the sandbox analysis. So this is kind of where we are now. The model that we built at our company, and again, this is not a sales pitch, it's just explaining how we built this. We started off with a 2 hidden layer system. We had one layer that looked for clean, one layer that looked for malicious. It was inefficient. The clean layer had 2.3 billion nodes. And what that means is it just went out and it looked for those indicators only. And it was connected to the next layer, which had 3.2 billion nodes. So every time we added a node in one, we had to create 3.2 billion connections. Imagine adding 50,000 new nodes. It was very inefficient. So we took that stack of features and we marked them as malicious or clean indicators and built a single layer. So now what happens is one operation. A node goes out and it'll grab a feature. Oh, this is clean. And it goes in that file and it looks for those 1s and 0s. And if it finds it, it passes forward a value. Malicious, clean, picks these up. Currently, this is around 15 billion nodes in our system. We have 15 billion code blocks that we use to analyze. Now, this is the static side of being able to go offensive on cyber criminals. So it's extremely scalable, fast, et cetera. And by the way, it took us 5.5 years just to build out the feature set for this, to train this artificial intelligence system. So what happened as a result of us doing this, we also added an AI that automatically generates those super signatures for us. And we tested it to see how efficient it was. And this is a 74-day run, recent run, to see how much we picked up off that our competitors did not on ST3. So the highest occurred around 2 days prior to the rest of them getting it. But all the way out to 74 days, we were picking up 0-day attacks that our competitors hadn't. And it's because those code blocks, they get reused by cyber criminals. That's where we want to hit them at and be able to recognize it immediately. So that's one part of our offense. And by the way, this is relatively new. This was only given to me a couple of days ago, the analysis. Most of it that we caught, by the way, were Trojans, banking Trojans. There were some different things like ad loaders, different types of malware families, et cetera. This big blue box here, we're still investigating, trying to figure out what that consisted of. So like I said, this is relatively new information. So now here's part one of this offense against cyber criminals, that static attempt to determine what they're doing within your systems. So the next thing we can look at that we daisy chain within our operations view of being on the offense is a dynamic analysis of cyber criminal activity. And what we do here is we use the standard attack methodologies to analyze what they're trying to get to. There are different foundational approaches to describing the chain of events that lead to malware being inserted within systems. It's the kill chain, if you will. One of the more popular kill chains is MITRE. It's very descriptive. How many people here know about MITRE? There's a few, okay. Anyways, it's very, very descriptive, very detailed, and a very powerful framework to analyze malware against to see what it's really trying to do. We have these within the attack side of it. We have different steps that malware takes to be able to be successfully implemented within your environment. The initial access, execution, persistence of it, et cetera. These are all the steps that malware takes. Now, if we were to look at the MITRE framework in relation to those steps, we have very, very prescriptive, very detailed information about how that attack is unfolding or what's being used within this attack framework to allow this malware to exploit your systems. For instance, under credential access, we have account manipulation, bash history, brute force. Within each one of these, there will be hundreds of thousands, potentially, different hashes that are associated with the specific activities that are taken by that malware to accomplish a brute force attack against your systems. And these are all little code blocks, again, that do this, right? Little jumps within that program, within that malware program. So what does this really mean? It means that if we get a piece of malware, and the most recent one that we applied this to in our labs up in Vancouver, British Columbia, in Canada, was the orange worm attack. And we went ahead and tore it apart manually, and we ran it against the MITRE framework. And we had these different chunks of code that we found that fit underneath the MITRE attack framework, generally speaking. Now, this is good, this is fine, but to manually do this every time you're attacked by something that may be of interest is horribly intense from a labor perspective. It takes a lot. You typically have to rely on research labs to provide this level of information to you, or at least you used to. So let's talk about sandbox analysis using artificial intelligence and how that's used on the offense against cyber criminals. Our sandbox solution uses two analyses. When a file comes in, there's another static look that's taken. And again, we look at what type of a file it is. Is it a PDF? Is it a simple macro? Is it a Word document, Excel, whatever it is. And according to the unpack, unwrap analysis of what we can see, we give it an initial rating within our engine. Then we go ahead and detonate it. We extract all the behaviors in the sandbox log. The behaviors are sent to an AI rating engine, and the behaviors themselves provide us with a 3D cube, if you will, of a data point that associates to clusters of associated malware or clean files within the system. So it's unique to this sandbox, and it adds up all these scores, determines its placement within this three-dimensional model to give not only if it's malware or not, but the associated families, the associated code blocks that were discovered within it. And we use a Bayesian algorithm to create a radian data point within this structure. This is what provides us with insight as to where this malware possibly came from, what it was meant to do. So this additional analysis that was provided by the AI engine within this sandbox is now sent out to determine what particular pieces of execution within that MITRE framework were used in this attack, and also the severity of it, which means that now we can look at the critical versus non-critical type of attack pieces within MITRE automatically and backtrack out to determine what exactly the cyber criminals were trying to get at. They probably didn't succeed because we spotted the code blocks up front on the AV engine. But this additional analysis gives your engineers now the ability to actually backtrack and backtrace to the cyber criminal organization itself if you're provided with the correct data as far as their campaigns and their movements, etc. But you can certainly use this to determine what's being attacked and where to apply your security spending, your controls. Where do we want to focus our attention? What were they trying to do? What was their intent? How far did they get? A lot of times we know we can't patch and update everything. It's just impossible. It's a fool's errand to think that we can keep everything up to date. But if we can see them trying to attack and how they're attacking it, we can apply appropriate controls. So this is another insight into the cyber criminal activity. The really cool part comes in from when we start taking this machine learning and linking it within our environment. For instance, what we've done is we've created a system, whereas we're connected out to the internet with a couple of different systems, let's say on our perimeter. We may have the firewall, or we may have a email protection implementation out there. And they have that AV, AI protection, the CPRL signatures we talked about, built into it. So we have that as a service almost, running in the background of these products. And it doesn't matter. It could be one, it could be a dozen, but we have this AV baked into a lot of products. So let's say that we get a suspicious result out of here. It blocks it because you told it anything over 50% surety, kill it, we'll take a look at it maybe. Well, to take a look at it happens automatically now through our Sandbox implementation. It fires it into the Sandbox, and the MITRE attack framework that I showed you earlier is automatically produced for engineers. So we have AI systems that are feeding results into an AI-powered system to give you further granularity and clarity into what's going on within your environment. Again, that's kind of cool, but not really what you'd call much of an offensive analysis, really. I mean, you can dig through and see what they're trying to get through. So we took it to another level. We've started using AI in campaign analyses of cyber criminals. The silence group was one that we recently completed. And the silence group is a criminal organization that was responsible for 5 major campaigns. They had 436 indicators of compromise that we could associate back to their specific software, into the things that they had engineered and produced. They went after 15 vulnerabilities, and their attack patterns, we came up with 86 general attack patterns that we could associate directly back to them. So what we did with this knowledge is we applied it to that MITRE attack framework again. We looked at the criteria to determine if a specific group meets our candidate requirements or not. And that means that they had to have so many campaigns, so much activity, that we had enough knowledge on them to be able to build this out into a data structure. The next thing we did was collected all of the information we can. Went out to ST3, OSINT, YAR rules. We have around 500,000 sensors around the planet we collect things from. We are tied out into 140 public sticks, et cetera, that we collect information from. We also have a cyber threat alliance, which is, here's a weird little science experiment for you guys. So we went out to our competitors, Palo Alto and Cisco and Checkpoint and all these guys, and we created a consortium to where we all share threat intelligence amongst ourselves. And every week, the group votes on what any one organization provided, and if it's like they're putting in 50 cents and pulling out $5, you get voted off the island. So it's actually kind of fun to watch. Everybody's scrambling to make sure they're keeping their workload up. But anyway, so we collect all this information up. Then we do the analysis, and we do the baseline discoveries, Maltego analysis, different types of looks at it to see if we can figure out hashes and clusters and relationships between this malware and its sourcing. Now, right now, this is all manual labor. We're training an AI to be able to pull in all of this information and actually associate malware outbreaks with specific groups based off of these. You remember the pattern of malware versus clean that I showed you earlier? We're actually using that to associate cyber criminal group and organization behaviors and activities. So anyways, then we look at the, we research it and plug it into the MITRE attack framework and disseminate it out to our early partners. We do public releases, And that's all fine and interesting. I mean, that's something any good citizen of the security industry would do for their customers. However, in the background, what we're doing is a little bit more further analysis within this group. I talked about Silence earlier. They're a criminal organization. They're basically looking for financial exploitation of ATMs. They do a lot of jackpotting. Jackpotting is where you'll spearfish or break into that ATM, and then you'll have mules come by and pull money out of it. So the entire operation is was weaponized in these delivery vehicles. Bank officials were phished. Even organizations that provide servicing to the ATMs, they run around putting in cash, et cetera, were targeted in these phishing campaigns. So anyways, there were a variety of different methods and ways that were used, but basically that was their main operation. The Silence group was big on jackpotting. You heard about the one where there was 500 million or something pulled in a matter of 24 hours. It was like a year and a half ago. This was the group that was behind that globally. So anyways, we came up with the specific attack parameters that they used within these jackpotting schemes, and then started watching general migrations of code blocks as they associated with changes in the group's attack patterns and methods of attacking these ATMs. We observed activity in Australia, Canada, and France, Ireland, Latvia, Netherlands, Poland, Spain, Sweden, and the USA. And we actually were able to build cluster maps based off of the locations of the attacks from a local and global perspective, and come up with probable location within the dark web of their CNC servers and things like that. So we built quite a background database on them as far as the intelligence gathering. So then what we did was we took the individual campaigns and we started plugging them into the MITRE attack again, this framework, which means that at this point we have the ability to now dig deeply in for specific patterns, MD5 hashes of code blocks, as well as those general patterns of attack, and associate them back to the cybercriminal groups. We're plugging this into an artificial intelligence engine for the purpose of being able to predict their next moves and come up with probabilities of where they'll attack and how they're going to do it. And it's actually proving to work. We're seeing results with this now. This isn't commercially available yet. It's in development stages. It'll probably be another year of training before this is released out. So right now we're tearing manually, we're tearing these attack methods apart manually, teaching an AI to tear it apart and extract this specific information. Then we have another AI machine that's doing the association of that extraction back to specific cyber groups, cyber criminal groups, so that we can track them and their behavior in a proactive manner. This intelligence is going to be disseminated out to security professionals as part of an early warning system, if you will, of expected probabilities of where and how the next attacks will come from these types of groups. We're doing it across multiple groups, certain size, certain parameters that get met, we select them, and we analyze them. So artificial intelligence is in the background, proactively grabbing code blocks for a static analysis. Then we're grabbing, in a sandbox, malware breakdowns and patterns of attacks to be able to associate it back to your systems. Then we're extracting that information further back into looking at patterns of attacks that relate to specific cybercrime, cyber criminal groups around the globe. So where are we? AI capabilities currently that we've built out. This AV system, I told you about, the static. And by the way, AI is the most blah, blah, blah thing in the universe right now. Does anybody ever play BS Bingo? Do you know what that game is? It was really funny. When I first got into IT 20 years ago, security 20 years ago, we'd go to conferences. And some clown like me would be up on the stage going, well, you have to synergize and think out of the box to be able to, and there's all this blah that doesn't mean anything. Well, we built these little cards that had, think outside the box and strategize and all these key words, and we'd put them on a bingo card. And as he went through and said these key BS terms, we'd mark it off, and whoever got 5 in a row wins. They'd stand up and yell bingo in the middle of the speech. 23 people would laugh. 100 people would wonder what's going on, And AI right now is pretty much like that. Everybody comes in and they start talking about artificial intelligence and what they have. There's a couple of points to be made about that. Deep data, discoveries, and things like that. That's not AI, that's just simple algorithms. And the other thing is that these systems cost a lot and take a long time to implement. IBM is the master of AI. They came out with Deep Blue and Watson and things like that. When I was a little kid, which was many centuries ago before dinosaurs were oil, I used to watch Crazy Bobby Fischer, the world champion chess player, go up against Kasparov, the Russian chess giant. And I saw Deep Blue beat Kasparov. And IBM took Deep Blue and they kept working on AI, and they went up to Watson. It's what we understand now and we see on TV a lot. They recently tried to train an implementation of Watson to recognize cancer types, the stage, and provide medical recommendations on how to treat it. The problem is they used compressed data sets and accelerated the training of it into a very, very short span, thinking that it would be okay. And they showcased it at a big hospital in Boston back in the US. And it was a miserable failure because of the acceleration, et cetera. So these AI systems are not trivial to build. Anyway, so within this AV structure I talked about, where we just pull out those code blocks, static code blocks, there's actually 3 AI engines in there. The first one tears malware apart and plays with the golf ball stack of features, moving them up and down based off of how often it sees these specific pieces and how relevant they are to the problem. We have another one that builds those super signatures. It sorts out new, interesting features from everything coming in and builds out these super signatures. Then we have a third one down there, Clyde, and what he does is he provides quality assurance to what this guy produces. The second one that we talked about, the Sandbox, artificial intelligence, does a static and dynamic, 2 AIs built into that. We have another one in the background that goes out every night and looks at URLs, any new URLs within the internet. It takes net new and it runs through a huge analysis using letter replacement for the entire string. 1 letter for a letter for a number, a letter for a special character. And it runs the entire string against known patterns. And then it goes back through and it looks for sourcing, ownership, who is information, et cetera, everything that it can pull. And it takes all of this and puts it back into that data cube and relates it out to whether a site is malicious or not, but it also relates it back to the organizations and cyber criminals that own that particular URL or are suspected of owning it. And so it's another relational piece that we plug into this. We have, we're actually building a AI system that'll be a standalone box that sits on networks. This is kind of cool. It takes, you remember that golf ball stack of features? The most important one's up at the top. It takes a slice of that off and uses it for an on-site static analysis. Then it also takes all of your traffic, all of the files, in a training mode and learns what type of traffic and files are normal for your environment and starts to build out the malicious and clean feature sets locally. Then we have adaptive endpoint learning. We have another one that sits on your phone or server or whatever, and it does a 2-week learning of normal behavior and then starts picking up potential anomalies. And it works on network traffic, open ports, activity, time zones, even websites that are looked at by the individual. You take up fly fishing or what's the latest one? Aqua gardening. Does anybody do aqua gardening in here? No? You? Yeah. So everywhere I've gone, I've met people that do. I didn't know what it was until 2 days ago. But anyway, so you start surfing new sites. What it does is it creates bubbles of normalcy that you can play within. Now, there are big no-nos that it alerts on, like you're trying to gain unauthorized access, or all of a sudden you're downloading a ton of files you shouldn't. That's the dumb stuff. What we're looking for is very subtle, anomalous behavior within that user base or the server platform. But anyway, so these are systems we have up and running now. What about cyber criminals? And where are they at? And by the way, these are all linked together to provide that kind of offensive outlook. And it's also feeding that larger AI system in the background that we're building for cyber criminal organization identification and hopefully eradication. We're looking to get rid of them. The whole point of all of this is to make it too expensive for cyber criminals to be able to attack your organization. Anyways, I've got 10 minutes. So I often get asked, what about the cyber criminals? What are they doing? Most places I go to, somebody will invariably say, well, when do you think the cyber criminals are going to start using AI? And it's already happened. A friend and I were kind of snooping around the dark web a little bit into a chat room on layer 6 or so. And sure enough, they're shopping for skills. You know, on the darknet you can get humans and guns and drugs and everything. Well, this was a skills kind of a sharing where people could get hired for providing services. And a question popped up on the board saying, I need somebody with strong Python and AI background. Who's got it? And within a couple of minutes, bink, 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 there were 4 or 5 answers right away. Yes, I built AI systems. I've done this. Here's what I charge per hour in Bitcoin, or whatever they were using for the base. Give me a ring back. And so cyber criminals are already building AI systems. What are they mainly doing with it? The first one is AI fuzzing and zero-day mining. Fuzzing is low-level attacks typically against a system to try to determine if a series of these low-level attacks will provide access, break the system to where you can penetrate and establish your foothold. So AIs are being used to fuzz systems already. And it's fairly easy to do if you think about it, because the vulnerabilities, the CVEs are all published out there. You train a system to do the basic attacks with all types of open source software or things available for purchase. And basically you can train a system fairly quickly to fuzz an Apache implementation or whatever you have, a SQL server. The other thing that they're interested in is machine poisoning. And this one's kind of interesting from my perspective, because you remember that golf ball stack of features that I talked about? That's the real gold of an AI system. They're stacked in their order of importance within the system. If you can insert false information into that stack, you subvert the ability for the AI system to provide the correct solution. For instance, there was a system that was recently built that recognized dogs, and it would recognize crossbreeds of dogs. And they were demonstrating it. And they put up a picture of a husky and let the thing, and it said, wolf. A little embarrassed, they got another picture of a husky and fed it in. Came back as wolf. And they found out that they were training it what was, the things that weren't dogs. Cats and ferrets and rats and mice and giraffes and wolves were in there as well. But when they fed it pictures of wolves, there was always snow in the background. The husky pictures all had snow in the background. And it subverted that data stack to give wrong information, or so the AI was led down the path of providing wrong information. That's a form of AI poisoning, stack poisoning. And cyber criminals are trying to figure out how to send files into systems like I described before that have inserted pieces within it to throw the AI off and put in things in importance in orders that aren't necessarily relevant to the problem being addressed. The last one is swarm technology. We're starting to see AIs implementing low-level AIs being implemented within swarms. And what they're able to do is autonomously change targets, change attack methods and techniques based off of the intelligence they collect and share amongst that small swarm. So, I hope I gave you some insight on where this is going with this whole cybersecurity AI picture on the offense. What we want to do, again, is make it too expensive to be a cyber criminal, or make them get so creative it takes them longer to get to the table for their attacks. Currently, just with those code blocks that we're extracting, the URLs that we extract, the information that we link everything to, we're getting into the point of being able to predict their behavior. And this is where we want to go to with this whole artificial intelligence movement, and being able to offensively track down these rings and deal with them. Stuff to remember. Like I said earlier, it's not trivial. If somebody comes in and pitches AI and they're like, yeah, last year we made one and it's really cool and it does everything, it bakes bread and it'll wash your car and feed your dog. No, that's not how it works. This particular system that we built took us 10 years to get it to a maturity state today to where that accuracy is extremely high. It was 5.5 years just to train the system. And that took a lot of people, money, technology, a huge investment. So it's not trivial. The other thing is it should ease technical resource demands and build trust within your organization. If you're implementing an AI and you have to watch it and tell it what's right and what's wrong, it's probably one of those 5-minute, quick bake solutions. Again, AI isn't something that you just throw in the air and it pops out into something pretty and lands on the floor. It takes a lot of effort. As a point-specific solution, AI is extremely limited. When you start connecting them and sharing that information across different platforms and building more and more of these layers that have responsibility to find something, and you join those layers into a result, this is where AI gets to be powerful. The single point solutions of being able to find malware through that AV system that I described, I mean, it's nice, it's cool, it works, but the real power of AI is in the connection of it, feeding the output data into another AI system, This is where you start getting the surety of results that you need with it. Anybody that pitches it without some knowledge is probably just doing that BS bingo kind of thing on you. So be careful of it. Now, I always get asked this at the end as well. Where's AI at and where's it going? Right now, we're in the dumb pet trick stage of AI. It does complex things. It flies drones around the globe at hypersonic speeds a dozen times and lands it on a carrier in the middle of the Pacific. Drives cars, all kind of things. But we're still at this very, very brick dumb kind of level of artificial intelligence. The second level is going to be where it's healing its own code, writing its own code to improve itself. The third stage of AI comes in when the AI wakes up in the morning and gets lazy and decides it doesn't want to go to work, so it creates another AI to do its job for it. This is going to require vast amounts of computing power. I think there's going to be a convergence of technologies in this field, and it's going to be around quantum computing and AI coming together. I saw an article the other day that there was a solution found to quantum fuzziness, if you will. Schrodinger's cat experiment, where you don't know until you look, it could be either state, plagues the implementation of quantum computers today. That and room temperature, commercially available superconductivity for the systems. Once we solve those two issues, we'll see quantum computing kick off, and that means billions of times of compute power within the same or smaller space now will be available to us. I think at that point, we will be able to build the AIs that take the ability to do tasks such as getting up out of my presentation thinking, he's an old guy, that was kind of fun, I guess, and getting a cup of coffee. All the balance, the proprioceptive input, jostling in line, seeing who's moving where, billions of little computations are going on as you go get that cup of coffee. For us to be able to build intelligent systems that can do things like that, make those kind of decisions and implement them, will require billions of layers that consist of billions or possibly trillions of nodes. So anyways, there's the background, my knowledge of AI and how it's going to be applied for the offense in the security industry. I hope you enjoyed the talk, and I really do appreciate your time and you being here. Thank you so much.